Have you ever stopped to think about how long it would actually take to travel to the planets we can see in the night sky? Not in some vague science fiction sense, where ships zip across galaxies in the blink of an eye, but in real, measurable human time. Days that stretch into weeks, weeks that become months, months that bleed into years or even entire lifetimes. We're going to explore the actual duration it takes to reach every world in our cosmic neighborhood, from the scorched surfaces closest to the sun all the way out to the frozen giants lurking at the very edge of our solar system, and then we'll push even further into the unimaginable distances that separate the stars themselves. By the time we're done, you'll understand what it truly means to travel across space, and why the universe is far more patient than we could ever hope to be. This is the real timeline of interplanetary travel, and it's going to change how you see the night sky forever. When most people picture the solar system, they imagine a neat arrangement of planets lined up like pearls on a string, evenly spaced, orderly, and perfectly reachable. That mental image comes from the diagrams we all saw in school, those colorful posters showing Mercury, Venus, Earth, Mars, and the rest arranged in a perfect row from left to right, each one a comfortable distance from its neighbors. But those diagrams are deeply, fundamentally misleading. They compress unimaginable distances into something that fits on a classroom wall, and in doing so they hide the most important truth about space travel. The planets are not close together. They are separated by gulfs of emptiness so vast that our fastest machines would take months or years just to cross from one to the next. Space is not a highway with exits every few miles. It's an ocean so wide and so deep that the nearest island might be half a year away at full speed, and there's nothing but silence and absolute darkness in between. Let's start with something familiar to build some genuine perspective before we go further. The moon is the only celestial body humans have ever walked on. It orbits Earth at an average distance of about 384,000 kilometers. That sounds like a lot, and it genuinely is. It's nearly 10 times the circumference of our entire planet wrapped around itself. If you could somehow drive a car to the moon at normal highway speed without stopping for a single second, it would take you about 6 months to get there. But we don't use cars for space travel. We use rockets, the most powerful machines human beings have ever constructed. Even so, it still takes about 3 days for a spacecraft to travel from Earth to the moon. 3 full days of continuous flight to cover a distance that, in cosmic terms, is practically nothing at all. The moon is right next door by any astronomical measure, and yet it takes 72 hours of burning engines and silent coasting to reach it. That's how slow we are compared to the true scale of space. Now think about Mars. Mars is talked about constantly as humanity's next great destination, the planet we'll colonize within our lifetimes, the world that will become our second home, and the first step in our expansion as a spacefaring civilization. You've heard the promises from space agencies and billionaires alike. We're going to Mars, we're going soon. But here's what those conversations often leave out. Mars, even at its absolute closest approach to Earth, is still about 55 million kilometers away. That's more than 140 times farther than the Moon. And Mars isn't always that close. Most of the time, it's much farther away than that, because both planets are constantly moving through their orbits at different speeds. When Earth and Mars are on opposite sides of the Sun, the distance between them swells to over 400 million kilometers. That's more than 1 billion times the length of a football field. So when we talk about going to Mars, we're not talking about a quick trip. We're talking about a journey that takes between 6 and 9 months, depending on when you launch, and how efficient your trajectory is. 6 to 9 months of floating through the void, sealed inside a pressurized metal tube, breathing recycled air, eating carefully rationed food, with nothing outside your window but stars that never seem to move no matter how fast you're going. But here's the thing that most people genuinely don't realize until they sit down and think carefully about it. Distance in space isn't measured the way we measure distance on Earth. On Earth, if you want to know how far away something is, you measure it in kilometers or miles and you're done. The number is manageable, it fits in your head, you can imagine it. But in space, those units become useless almost immediately. The numbers get too big, too unwieldy, too divorced from anything you can picture. So astronomers over the centuries invented new units of measurement that scale appropriately to the task. The first of these is the astronomical unit, abbreviated AU. 1 AU is defined as the average distance from the Earth to the Sun, which works out to about 150 million kilometers. That's the distance light travels in roughly 8 minutes, which itself gives you a sense of the scale. So when scientists say that Mars orbits at about 1.5 astronomicals from the Sun, what they mean is that Mars orbits at 1.5 times the distance between Earth and the Sun, about 225 million kilometers from the star at the center of our system. Mercury orbits at about 0.4 astronomicals, much closer to the Sun, and bathed in far more intense heat and radiation. Neptune, the farthest recognized planet in our solar system, orbits at about 30 astronucleates from the Sun. That's 30 times the distance from Earth to the Sun, 30 times 150 million kilometers, which works out to roughly 4.5 billion kilometers. The numbers stop making intuitive sense very quickly, and we haven't even left our own solar system yet. And then, when you leave the solar system entirely and start talking about the distances to other stars, even the astronomical unit becomes too small a unit to be useful. That's when we switch to light years. A light year is defined as the distance that light, moving at approximately 300,000 kilometers per second, travels in 1 full year. That works out to about 9.5 trillion kilometers. It's a number so large, it's essentially meaningless to the human brain without some kind of reference point. Our nearest neighboring star system, Alpha Centauri, is 4.37 light years away. That means that if you could somehow travel at the speed of light, which nothing with mass can do according to our current understanding of physics, it would still take you more than 4 years to reach the nearest other star. More than 4 years traveling at the fastest possible speed the universe allows. And we cannot travel at the speed of light. Not even remotely close. The fastest spacecraft humans have ever built is the Parker Solar Probe, a NASA mission launched in 2018 to study the Sun up close. As it falls toward the Sun and is accelerated by solar gravity, it reaches speeds of about 700,000 kilometers per hour. That's fast enough to travel from New York to Los Angeles in about 15 seconds. It sounds impossibly fast until you realize it's still only about 0.064% of the speed of light. At that speed, traveling in a straight line to Alpha Centauri, it would take over 6,500 years to get there, 65 centuries of continuous flight. That's longer than all of recorded human history from the earliest writing systems to the present day. The pyramids of Egypt were built about 4,500 years ago. Traveling at the speed of our fastest spacecraft, we wouldn't even be halfway to the nearest star yet. So when we talk about traveling to the planets, we're not really talking about distance in the traditional sense at all. We're talking about time. Time is the fundamental currency of space travel. Every mission is measured not primarily in kilometers, but in how many months or years it takes to get from here to there. And even the closest destinations, the ones that seem practically next door on a solar system map, require more time than most people have any intuitive feel for. Let's walk through them one by one, starting with the planet closest to the Sun and working our way outward through the solar system and eventually beyond into the space between the stars. Mercury is the smallest planet in our solar system and the one that orbits closest to the Sun. On average, it's about 77 million kilometers from Earth, which might make it sound like it should be a relatively easy destination to reach. After all, that's much closer than Mars. But here's the thing that makes Mercury one of the hardest destinations in the entire solar system to actually visit. The problem isn't distance. The problem is orbital mechanics. And orbital mechanics has a cruel sense of irony. When you leave Earth, you're already moving at the same speed. Earth is moving around the Sun, which is about 30 kilometers per second, or roughly 108,000 kilometers per hour. That's just the speed you inherit from Earth's orbit before your rocket fires a single engine. To reach a planet that's farther from the Sun than Earth, like Mars or Jupiter, you use that existing speed and add more. You accelerate outward, and the Sun's gravity curves your path into an arc that carries you to the target planet. The physics is relatively straightforward, at least in concept. But to reach Mercury, which orbits closer to the Sun than Earth does, you have to do the exact opposite. You have to slow down. You have to shed enormous amounts of speed to fall inward toward the Sun, fighting against the momentum you inherited from Earth's orbit. And shedding speed in space is just as hard, if not considerably harder, than gaining it. There's nothing to brake against. You can't press the clutch. Every bit of speed you want to lose has to be cancelled out by engine burns or stolen by the gravity of other planets, and both approaches cost fuel, time, or both. The first spacecraft to visit Mercury was Mariner 10, launched by NASA in November 1973. The mission designers knew they couldn't afford to fly a direct path, so they sent the spacecraft on a curved trajectory that first took it past Venus. By flying close to Venus and letting that planet's gravity bend its path, Mariner 10 was able to slow itself down just enough to fall into an orbit that would intercept Mercury. This technique is called a gravity assist, or sometimes a gravitational slingshot, and it's one of the most ingenious and important techniques in all of spaceflight. The basic idea is that by swinging past a planet at the right angle and speed, a spacecraft can steal a tiny fraction of that planet's enormous orbital momentum, using it to change its own speed and direction without burning any additional fuel. Mariner 10 used Venus as a brake, slowing down enough to reach Mercury's orbital path. It arrived at Mercury in March 1974, about 5 months after launch, but it couldn't stop. It passed Mercury 3 times, taking photographs and measuring the planet's magnetic field and thin atmosphere, before drifting away into a solar orbit. The spacecraft had no way to slow itself down enough to enter orbit around Mercury. It simply didn't carry enough fuel. It would be more than 30 years before humanity made another attempt to visit Mercury. In August 2004, NASA launched a spacecraft called Messenger, which stood for Mercury's surface, space environment, geochemistry, and ranging. It was designed to be the first probe ever to enter orbit around Mercury and study it in sustained detail. But even with far more advanced technology than Mariner 10, the journey was extraordinarily long and complicated. Messenger didn't arrive at Mercury and achieve orbit until March 2011, nearly 7 years after launch. Why did it take 7 years to travel to the closest planet to the Sun? because it had to perform no fewer than 6 separate gravity assists along the way. 1 flyby of Earth, 2 flybys of Venus, and 3 flybys of Mercury itself. Each one carefully calculated to reduce the spacecraft's speed just enough to eventually be captured by Mercury's gravity rather than flying past it. 7 years of patient maneuvering through the inner solar system to cover a distance of 77 million kilometers. That's the reality of space travel. It's not about distance in any simple sense. It's about speed, timing, gravitational geometry, and the invisible hand of orbital mechanics that governs every move every spacecraft ever makes. The most recent mission to Mercury is called BepiColombo, a joint project between the European Space Agency and JAXA, the Japan Aerospace Exploration Agency. It launched in October 2018 and is scheduled to finally arrive at Mercury and enter orbit in late 2025, making the total journey time once again about 7 years. Along the way, BepiColombo is performing 9 planetary flybys, 1 past Earth, 2 past Venus, and 6 past Mercury itself. Each flyby precisely adjusts the spacecraft's trajectory, shaving off just the right amount of speed at each encounter. The mission is actually carrying 2 separate orbiters that will separate and enter different orbits once they arrive, one to study Mercury's surface and composition, and one to study its magnetic field and magnetosphere. It's one of the most technically complex missions ever attempted by any space agency, and it illustrates perfectly just how hard it is to reach a world that looks so simple and close on a diagram. So what's the actual travel time to Mercury? For a flyby mission like Mariner 10, you can reach Mercury in about 5 months with the right alignment and trajectory. But for an orbital mission that actually stays at Mercury and studies it, the timeline stretches to 6 or 7 years because of the fuel requirements involved in slowing down enough to be captured. And a landing mission, which has never been attempted, would require even more time and fuel to decelerate gently enough to touch down on the surface without crashing. Mercury might look close on the map, but it's one of the most energetically expensive destinations in the solar system. It's a vivid reminder that in space, the shortest distance between 2 points is almost never a straight line, and the nearest destination is not always the easiest one to reach. Now, let's turn our attention outward from the Sun's immediate neighborhood to Venus, the second planet, Earth's so-called twin, and in many ways the most fascinating and underappreciated world in our solar system. Venus is almost exactly the same size as Earth, with a diameter about 95% of Earth's. It has nearly the same gravitational pull at its surface. It orbits at a distance from the Sun that puts it solidly in the zone where liquid water could theoretically exist. In many ways, when our solar system first formed, Venus may have been very similar to Earth, possibly with oceans, possibly with a more hospitable atmosphere, possibly even with the early conditions needed for life. We don't know for certain. What we do know is what Venus looks like today, and today Venus is a nightmare. The surface temperature on Venus is about 465 degrees Celsius, which is 869 degrees Fahrenheit. That's hot enough to melt lead. It's hot enough to destroy most metals and ceramics within hours. The atmospheric pressure at the surface is about 92 times greater than Earth's atmospheric pressure at sea level, which is roughly equivalent to the pressure you'd experience about 900 meters underwater in Earth's oceans. The clouds that make Venus look so beautiful and bright in the night sky, the clouds that make it the third brightest object visible from Earth after the Sun and Moon, are not made of water vapor. They're made of concentrated sulfuric acid droplets. The wind at the surface is relatively gentle, but the combination of crushing pressure, searing heat and corrosive chemistry makes Venus the most hostile planetary surface in the solar system, worse in many practical ways than the airless vacuum of space. Despite this, Venus holds a special place in the history of space exploration because it was the first planet beyond Earth that spacecraft actually visited in any meaningful way, and it remains one of the fastest destinations we can reach with current technology. The quickest trip ever made by a spacecraft to another planet was to Venus. In August 1962, NASA's Mariner 2 spacecraft launched from Cape Canaveral on an Atlas Agena rocket. On December 14, 1962, it flew past Venus at a distance of about 34,000 kilometers. The total journey time was 109 days, just under 4 months. No mission to any other planet, before or since, has made the trip in less time. The combination of Venus's relatively close orbit and the favorable geometry of that particular launch window made for an unusually efficient trajectory. But what Mariner 2 found during that flyby shattered one of the most cherished hopes in planetary science at the time. Before the mission, many scientists genuinely believed that Venus might be habitable, possibly a warm, humid world covered in tropical forests beneath those impenetrable clouds. The science fiction of the era was full of stories set on a verdant, jungle-covered Venus. Mariner 2 ended that dream permanently. Its instruments detected surface temperatures of around 500 degrees Celsius and confirmed that Venus's atmosphere was overwhelmingly composed of carbon dioxide. There were no forests. There was no water. There was nothing on the surface that any form of Earth life could survive for even a fraction of a second. The Soviet Union was paying close attention to Mariner 2, and they decided that if they couldn't be first to the moon, they would be first to land on another planet. Between 1961 and 1984, the Soviet space program launched an extraordinary series of missions to Venus under the umbrella program name Venera, which is simply the Russian word for Venus. More than a dozen spacecraft were sent. Many failed before reaching the planet. Some were lost in the crushing atmosphere before they could transmit any data. But a handful succeeded, and what they sent back was extraordinary. Venera 7, launched in August 1970, became the first spacecraft in history to land on another planet and successfully transmit data from the surface back to Earth. It survived for 23 minutes before its electronics gave out in the heat. The temperature it measured at the surface confirmed what Mariner 2 had suggested from orbit, around 465 degrees Celsius. Venera 9, which landed in October 1975, sent back the first photographs ever taken from the surface of another planet. The images showed a landscape of sharp, angular rocks, nothing like the worn, rounded stones you'd see on Earth or even on Mars. Because there's almost no wind erosion on Venus's surface, rocks stay sharp for millions of years. Venera 13, landing in March 1982, sent back the first color photographs from the Venusian surface and managed to survive for 127 minutes, a record for Venus surface operations that has never been beaten and remains unlikely to be beaten anytime soon. Every single one of those Soviet landers was eventually destroyed by the environment. The heat soaked through the insulated shells. The electronics failed. The batteries died. The pressure crushed components not designed for it. The acid in the atmosphere attacked seals and surfaces. Venus kills spacecraft reliably and thoroughly. It's not a place you visit twice. It's a place you visit once, if you're lucky, for a few minutes before the planet takes you apart. So the travel time to Venus is relatively short. Most direct missions take between 4 and 6 months, depending on the trajectory and the position of the planets at launch. The 109-day record from Mariner 2 represents essentially the fastest you can get there under ideal conditions, using conventional chemical propulsion. Most missions take a bit longer because they choose trajectories that are slightly less fuel efficient in time, but save propellant, leaving more in reserve for maneuvering at the destination. Venus also plays a crucial role in missions headed elsewhere. Because of its position in the solar system, Venus is an ideal place to perform gravity assists. The Parker Solar Probe, which, as we mentioned, is the fastest spacecraft ever built, has flown past Venus multiple times. Each Venus flyby uses the planet's gravity to bend the probe's orbit closer to the Sun, gradually decreasing the perihelion, the closest point of approach, with each successive pass. Without those Venus flybys, the Parker Solar Probe couldn't reach the close solar distances it needs to achieve its science objectives. Venus is a hell of a planet, but an incredibly useful one from an orbital mechanics perspective. There are upcoming missions to Venus from multiple space agencies that will shed more light on this mysterious world. NASA's Da Vinci mission, planned for the late 2020s, will send an atmospheric probe into Venus's atmosphere to measure its composition in detail and image the surface through breaks in the cloud cover during the final descent. NASA's Veritas mission, also planned for the late 2020s or early 2030s, will map Venus's surface in unprecedented detail using synthetic aperture radar to see through the cloud cover. The European Space Agency's Envision mission will orbit Venus and study its geology and volcanic activity. None of these missions will land and survive. They'll do their science remotely or during a brief descent. But they'll tell us more about why Venus turned out so differently from Earth, and perhaps give us clues about how to prevent a similar fate here. The journey to Venus is quick. The science there is rich, but the planet itself remains one of the most inhospitable places we've ever sent machines, and the idea of sending humans there remains firmly in the realm of speculation. Now we come to Mars. If Venus is Earth's hellish twin, Mars is its frozen, thin-aired, rust-colored sibling who got shortchanged at birth. Mars is about half the size of Earth, with a surface gravity only about 38% of Earth's. Its atmosphere is 95% carbon dioxide, but is only about 1% as dense as Earth's atmosphere, thin enough to offer almost no protection from ultraviolet radiation and cosmic rays, thick enough to create dust storms that can cover the entire planet for weeks at a time. The average surface temperature on Mars is about negative 60 degrees Celsius, though it can swing from about 20 degrees Celsius at the equator on a warm summer day to negative 125 degrees at the poles in winter. It's cold, it's dry, it's irradiated, and it's lonely. And yet, of all the planets in the solar system, Mars is the one that feels most like a place humans could actually go to someday. Maybe even live on, maybe even call home. The reason Mars captures our imagination so completely is that it shows clear signs of having been very different in the past. Ancient riverbeds and lake sediments preserved in the Martian rock record tell us that liquid water once flowed across the surface in abundance. There was a time, billions of years ago, when Mars had a thicker atmosphere, a warmer climate, and liquid water pooling in lakes and flowing through river valleys. Whether life ever emerged in those ancient Martian waters is one of the most profound open questions in science. We might be on the verge of answering it. NASA's Perseverance rover, which landed in Jezero crater in February 2021, is right now collecting rock samples from what was once a lake and river delta system. Those samples If they ever make it back to Earth in the planned Mars sample return mission, could contain the fossilized traces of ancient Martian microbes, or they could confirm that Mars was always lifeless. Either result would be one of the most important scientific discoveries in human history. But before we can answer that question, before we can send humans to Mars or bring those samples back, we have to grapple with the basic reality of the journey. And the journey to Mars is not simple, it's not quick, and it's not forgiving of mistakes. Mars orbits the Sun at an average distance of about 228 million kilometers, which puts it at roughly 1.52 astronomical years from the Sun. Earth orbits at about 1 astronomical units, so the distance between Earth and Mars varies enormously depending on where both planets are in their orbits. At the closest possible approach, called opposition, or more specifically, perihelic opposition. When Mars is also near the closest point of its own elliptical orbit to the Sun, the two planets can be about 6 million kilometers apart. That's the Mars of science fiction promises. That's the Mars that appears in headlines when commentators say we're almost neighbors. But Mars at its farthest, when the two planets are on opposite sides of the Sun, is about 401 million kilometers away. That's more than 7 times farther than the closest approach. The average distance, averaged over many years and all orbital positions, is about 225 million kilometers. That's the Mars you actually deal with when you're planning a mission. Because both Earth and Mars are moving continuously around the Sun at different speeds, Earth completes one orbit in 365 days, while Mars takes 687 days. The two planets come into favorable alignment for spacecraft launches only periodically. These favorable periods are called launch windows, and they occur roughly every 26 months. During a launch window, the geometry of the two planets' positions is such that a spacecraft launched from Earth can reach Mars using a fuel-efficient trajectory in the minimum possible time. Outside the launch window, it's still theoretically possible to reach Mars, but it requires far more fuel or far more time, or both. Miss a Mars launch window, and you wait more than 2 years for the next one. The most commonly used trajectory for Mars missions is called the Hohmann transfer orbit, named after German engineer Walter Hohmann, who described it mathematically in 1925. A Hohmann transfer is an elliptical path that starts at one planet's orbit and ends at another's. The spacecraft is launched at a point in Earth's orbit, such that it arrives at the other end of its elliptical path just as Mars arrives at the same point from the other direction. It's a problem of exquisite timing, and getting it right requires calculations accurate to fractions of a second spread over journeys of hundreds of millions of kilometers. Using a Hohmann transfer orbit optimized for minimum fuel expenditure, the travel time to Mars works out to about 259 days, or roughly 8.5 months. Missions that are willing to spend more fuel to go a bit faster can trim that somewhat, down to about 180 to 210 days for many real missions. Missions that prioritize fuel savings over speed might take closer to 300 days. Looking at actual historical missions gives us a good bracket for what to expect. Mariner 4, the first spacecraft to successfully fly past Mars and return close-up photographs of its surface, was launched on November 28, 1964 and arrived at Mars on July 14, 1965. That's 228 days, about 7.5 months. The photographs it returned changed our understanding of Mars fundamentally. Instead of the canal-crossed, potentially inhabited world that some had hoped for, Mariner 4 showed a cratered, barren, moon-like landscape. 22 photographs, each taking about 8 hours to transmit back to Earth, showed a dead-looking world with no obvious signs of life, no liquid water, and a far thinner atmosphere than scientists had hoped. Viking 1, the first spacecraft to land on Mars and operate successfully on its surface, launched on August 20, 1975, and arrived at Mars on June 19, 1976, a journey of 304 days, just over 10 months. Viking 1 spent nearly a year orbiting Mars and mapping the surface from above before selecting a safe landing site, touching down on Cres Planitia on July 20, 1976, exactly 7 years to the day after Apollo 11 landed on the Moon. Viking 1 was the first spacecraft to transmit images directly from the Martian surface, and those first photographs of a rock-strewn orange plain under a pink sky became iconic images of space exploration. More recently, NASA's Mars Science Laboratory mission, carrying the Curiosity rover, launched on November 26, 2011, and landed in Gale Crater on August 6, 2012, a journey of 254 days. Curiosity used an entirely new landing system, a sky crane that lowered the rover on cables during the final moments of descent, a system so audacious it was called the 7 Minutes of Terror by the engineers who designed it. But it worked, and Curiosity has been operating on Mars ever since, climbing the layered sedimentary rock record of Mount Sharp at the center of Gale Crater, and finding repeated evidence that Mars once had extended periods of habitable conditions. NASA's Perseverance rover, launched July 30, 2020, and landing February 18, 2021, took 203 days, about 6.5 months, one of the shorter recent journeys. Perseverance carries the Ingenuity helicopter, which became the first powered aircraft to fly on another planet when it made its first flight on April 19, 2021. In its mission to collect rock samples for eventual return to Earth, Perseverance is carrying out what will ultimately be one of the most complex and expensive science missions in history, with the sample return mission expected to cost somewhere in the range of $10 billion. Now, what about future human missions to Mars? The travel time remains the central challenge. 6 to 9 months in space is an extraordinarily long time to keep human beings alive and healthy and psychologically intact. The physical effects of long-duration spaceflight on the human body are well documented from decades of experience on the International Space Station. Muscles weaken without gravity to work against. Bones lose density. The fluid distribution in the body shifts toward the head, causing vision problems in some astronauts due to increased pressure on the optic nerve. The immune system becomes dysregulated. The cardiovascular system deconditions. Returning astronauts from 6-month ISS missions often need weeks or months of rehabilitation before they can walk normally, and those astronauts had the enormous psychological comfort of knowing they were only 400 kilometers above Earth, well within rescue range, able to see their home planet out the window, able to talk to friends and family on the ground in real time. A crew bound for Mars would have none of that. Earth would shrink to a bright dot in the sky within a few weeks of departure. Radio signals from Earth would take up to 20 minutes to arrive each way, making real-time conversation impossible. In a genuine emergency, rescue would be months away, effectively meaning no rescue at all. The crew would be on their own in a way that no human beings have ever been in history. The radiation environment during the journey is also a serious concern. On Earth, and even on the International Space Station, which orbits within Earth's protective magnetic field, we're shielded from the most energetic cosmic rays and solar particles. On a trip to Mars, travelers would be exposed to the full flux of galactic cosmic rays, High-energy particles that stream in from supernovae and other energetic events throughout the galaxy, plus the risk of solar energetic particle events when the sun erupts and sends a burst of high-energy protons through the inner solar system. These particle radiation doses accumulate throughout the journey and increase the long-term risk of cancer and other radiation-related health problems. A Mars mission crew would receive roughly 300 to 600 millisieverts of radiation during the cruise phase alone, which is several times the NASA career limit for radiation exposure for astronauts. Solving the radiation problem is one of the most critical challenges for any human Mars mission. Despite all these challenges, the broad consensus among space exploration planners is that humans will reach Mars within the next 20 to 30 years. NASA's Artemis program, which aims to return humans to the Moon in the mid-2020s, is explicitly designed as a stepping stone toward eventual Mars missions. SpaceX, under Elon Musk's direction, has been more aggressive in its timelines, talking about crewed Mars missions by the late 2020s or early 2030s. China has announced ambitions for crewed Mars missions by 2033. Whether any of these timelines prove realistic is another question entirely, but the technology development is genuinely underway, and the political and commercial will to make it happen seems stronger now than at any time since the Apollo era. A crewed Mars mission, when it happens, will be a round trip that takes somewhere between 2 and 3 years total, 6 to 9 months to get there, a surface stay of roughly 18 months waiting for Earth and Mars to realign for the return journey, and then another 6 to 9 months to fly home. The crew members who volunteer for that mission will be away from Earth longer than any humans have ever been away from anything. They'll be making decisions with 20-minute communication delays, performing surgery and engineering repairs on their own, breathing recycled air, and eating food they've grown themselves, surrounded by nothing in every direction but the vast, silent, star-studded dark. And they'll be doing it for the right reasons. Mars is worth it. The science, the exploration, the challenge, and the sheer human drive to go somewhere we've never been before, all of it points toward Mars as the next great destination. The question isn't whether we'll go, it's when and what we'll find when we get there. Beyond Mars, the solar system changes character. The inner solar system, the region inside the asteroid belt, is rocky and warm, bathed in relatively intense sunlight. The outer solar system beyond the asteroid belt is a colder, darker, stranger place, dominated by enormous worlds of gas and ice rather than rock and metal, and the distances involved increase dramatically with every step outward. The asteroid belt itself occupies a broad region between about 2.2 and 3.2 astronomies from the Sun. It's commonly depicted in movies as a dense, dangerous cloud of tumbling rocks that spacecraft have to dodge carefully. The reality is completely different. The asteroid belt is vast, and the asteroids within it are spread so thinly that the average distance between them is roughly 1 million kilometers. If you were flying through the asteroid belt, you'd be astronomically unlikely to come within visual range of even a single asteroid without specifically navigating toward one. The total mass of everything in the asteroid belt combined is only about 4% of the mass of the Moon. It's not a solid ring of rock. It's mostly empty space with occasional rocks drifting through it. Despite that emptiness, the asteroid belt has been visited by multiple spacecraft. The Near-Shoemaker mission, launched in 1996, orbited and eventually landed on the asteroid Eros, becoming the first spacecraft to orbit and then land on a small body. The Dawn spacecraft, launched in 2007, used ion propulsion to spiral out through the inner solar system and eventually enter orbit around Vesta, the second largest body in the asteroid belt, in 2011, then spiral on to Ceres, the largest body in the belt and the only one large enough to be classified as a dwarf planet, arriving in 2015. The total mission took about 8 years. The OSIRIS-REx mission, launched in 2016, traveled to the near-Earth asteroid Bennu, spent 2 years in orbit mapping it in extraordinary detail, collected a surface sample by briefly touching down, and then returned that sample capsule to Earth in September 2023. The round trip took 7 years and delivered about 250 grams of pristine asteroid material that scientists are now studying in laboratories around the world. The asteroids are scientifically valuable because they're primitive remnants from the earliest days of the solar system, material that was never incorporated into a planet and has therefore preserved conditions from the solar system's formation 4.6 billion years ago. They're also potentially economically valuable in ways that are just beginning to be explored. Some asteroids are estimated to contain enormous quantities of metals, including iron, nickel, platinum, gold, and rare earth elements. The asteroid Psyche, which NASA's Psyche mission is currently traveling toward, is believed to be the exposed metallic core of a protoplanet that was stripped of its rocky mantle by ancient collisions. Its estimated metallic content, if it could somehow be brought to Earth, would be worth more than the entire global economy many times over. Of course, bringing it to Earth is not a realistic proposal, and the actual economic value of asteroid resources will only be realized if we develop the infrastructure to process and use those resources in space. But the potential is genuinely enormous. Beyond the asteroid belt, we reach Jupiter, and everything changes scale. Jupiter is not just the largest planet in our solar system. It's a world that dwarfs all comparison. Its diameter is 11 times that of Earth. Its mass is 318 times that of Earth. It's more than twice as massive as all the other planets in the solar system combined. If Jupiter had been about 80 times more massive, it would have become a star rather than a planet. It comes close enough to the boundary between giant planet and brown dwarf to make it genuinely remarkable. Its Great Red Spot, a storm system that has been raging for at least 350 years, and possibly much longer, is larger than the entire diameter of Earth. Its atmosphere, dominated by hydrogen and helium, shows a complex system of bands and zones, storms and anticyclones, auroras near the poles, and a faint ring system discovered by Voyager 1 in 1979. Jupiter orbits the Sun at an average distance of 5.2 asteroidal units, which translates to about 778 million kilometers. At its closest approach to Earth, when both planets are on the same side of the Sun, Jupiter is still about 588 million kilometers away. That's roughly 10 times the distance to Mars at its closest. The first spacecraft to reach Jupiter was Pioneer 10, launched in March 1972. It became the first spacecraft to cross the asteroid belt successfully and arrived at Jupiter in December 1973, a journey of 21 months. Pioneer 10 was essentially a pathfinder sent ahead to confirm that the asteroid belt wasn't too dangerous to cross, and that a spacecraft could survive the intense radiation belts that Jupiter is surrounded by. It managed to do so, though the radiation was more intense than expected and nearly overwhelmed its systems during the closest approach. Pioneer 11 followed in 1974 and arrived at Jupiter in December 1974, also about 21 months after launch. Both Pioneer spacecraft were simple spinning probes carrying a handful of instruments and famously bearing gold plaques designed to identify their origin to any extraterrestrial civilization that might someday intercept them. These plaques showed a diagram of our solar system, a drawing of a hydrogen atom, and silhouetted figures of a human man and woman. The man's hand is raised in what was intended as a gesture of greeting. Whether any being will ever read those plaques is unknown. Both Pioneer spacecraft have now left the solar system entirely, drifting silently through interstellar space with their batteries long dead and their transmitters silent. The Voyager missions, launched in 1977, reached Jupiter faster than the Pioneers because they took slightly more direct trajectories. Voyager 1 arrived at Jupiter in March 1979, about 18 months after launch. Voyager 2 arrived 4 months later in July 1979. The images and data returned by the two Voyagers transformed our understanding of the Jupiter system. Io, one of the 4 large Galilean moons, turned out to have active volcanoes, making it the most geologically active world in the solar system. Europa showed a surface of cracked ice that strongly suggested a liquid water ocean underneath. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, showed evidence of tectonic activity in its ancient past. Callisto, the outermost of the 4, was one of the most heavily cratered surfaces ever photographed. The Galileo mission, launched in 1989, took 6 years to reach Jupiter, arriving in December 1995. Unlike Pioneer and Voyager, which were flybies, Galileo was an orbiter designed to study Jupiter and its moons from orbit over an extended period. During its 8 years in the Jupiter system, Galileo made close flybies of all 4 Galilean moons and confirmed the existence of a liquid water ocean beneath Europa's icy surface. The evidence was compelling enough that Europa became one of the top priorities for future solar system exploration. When Galileo finally ran out of fuel in 2003, it was deliberately plunged into Jupiter's atmosphere, both to conclude the mission with a final atmospheric measurement and to avoid any possibility that the spacecraft could contaminate Europa with Earth microbes if its orbit eventually decayed. The Juno spacecraft, launched in August 2011, reached Jupiter in July 2016 after a 5-year journey. Juno uses a polar orbit that takes it on highly elliptical loops from far above the poles down to within about 4,000 kilometers of Jupiter's cloud tops every 53 days. This orbit takes it through the radiation belts only briefly during each close pass, minimizing radiation damage to its electronics. Juno has been studying Jupiter's atmospheric composition, internal structure, magnetic field and auroras in unprecedented detail. Its observations have shown that Jupiter's famous bands and zones extend much deeper into the atmosphere than anyone expected, and that the interior structure of the planet is more complex and chaotic than the simple layered models of the past. Juno is still operating and has been extended multiple times to study not just Jupiter, but also its moons including Europa, Ganymede and Io. So the travel time to Jupiter ranges from about 18 months for a fast flyby trajectory to 5 or 6 years for an orbiter, following a more fuel-efficient path with multiple gravity assists. Somewhere between 1.5 and 6 years, depending on how much fuel you want to spend and how precisely you need to align the launch with the planetary positions. Beyond Jupiter, we reach Saturn, and if Jupiter is the king of the planets, Saturn is the jewel of the solar system. Saturn's ring system, visible even through a small amateur telescope from Earth, is one of the most spectacular sights in the solar system. The rings are made of ice particles, ranging in size from microscopic grains to chunks as large as a house. orbiting Saturn in a precisely flat plane. They span over 280,000 kilometers from the innermost ring to the outermost, yet they're less than a kilometer thick on average. If you scaled the rings down to the diameter of a football field, they would be thinner than a piece of paper. They're extraordinarily beautiful and extraordinarily thin at the same time. Saturn orbits at about 9.5 astronomicals from the Sun, nearly twice as far as Jupiter. In terms of distance from Earth at closest approach, that puts it at about 1.2 billion kilometers away. The Cassini spacecraft, a joint project between NASA, the European Space Agency, and the Italian space agency ASI, was launched in October 1997 and arrived at Saturn in July 2004, a journey of nearly 7 years. To get there, Cassini performed 4 gravity assists. Once past Venus in April 1998, again past Venus in June 1999, once past Earth in August 1999, and once past Jupiter in December 2000. Each gravity assist added velocity to the spacecraft, building up the speed needed to reach the outer solar system without requiring an impossibly large amount of fuel. By the time it arrived at Saturn, Cassini had traveled 5 billion kilometers along its winding path, far more than the straight-line distance between Earth and Saturn. Cassini spent 13 years studying the Saturn system in astonishing detail before the mission ended in September 2017. During those 13 years, it completed 294 orbits of Saturn, made 127 close flybys of Titan, discovered geysers of water vapor on Enceladus that implied a subsurface ocean, and became one of the most exciting astrobiology findings of the past generation, studied the ring system in more detail than any previous mission, discovered 7 new small moons, watched a massive storm huygens that erupted in Saturn's northern hemisphere in 2010 and grew to encircle the entire planet, and sent the Huygens probe into Titan's atmosphere in January 2005, where it descended for 2.5 hours before landing on the surface and transmitting data for 72 minutes. Titan deserves special mention because it's one of the strangest and most fascinating worlds in the solar system. It's the only moon with a thick atmosphere, a nitrogen-dominated layer of gas that's actually denser than Earth's atmosphere, despite the much lower gravity. Below the orange hydrocarbon haze, Titan has lakes and seas of liquid methane and ethane, fed by methane rain that falls from hydrocarbon clouds. The Dragonfly mission, planned for launch in 2027 and arrival at Titan in 2034, will send a rotorcraft lander to Titan to fly from site to site across its surface, studying the chemistry of a world where organic molecules, similar to those that preceded life on Earth, might be forming right now. Beyond Saturn, the solar system becomes genuinely remote. Uranus orbits at about 19.2 astronomicals from the Sun, which is about 2.9 billion kilometers. At its closest approach to Earth, Uranus is still about 2.6 billion kilometers away. Uranus is the 7th planet from the Sun and the first to be discovered in modern times, found by William Herschel in 1781 using a telescope he built himself. It's classified as an ice giant, a different category from the gas giants Jupiter and Saturn, because its interior is thought to be composed mainly of water, methane, and ammonia in a hot, dense, fluid state rather than the hydrogen and helium that dominate Jupiter and Saturn. Its pale blue color comes from methane in its atmosphere, which absorbs red light and reflects blue. Uranus is peculiar in another way. It's tilted on its side, with its axis of rotation inclined at about 98 degrees relative to its orbit. This means Uranus essentially rolls around the Sun on its side, with its poles pointing roughly toward and away from the Sun rather than up and down. During the Uranian summer at one pole, the sun shines almost directly overhead for decades at a time, while the other pole experiences decades of darkness. During the equinox, the sun shines over the equator, and the planet behaves more like a normally tilted world. The cause of this extreme tilt is believed to have been a massive collision with an Earth-sized body early in the solar system's history, an impact violent enough to knock the planet onto its side. The only spacecraft to have ever visited Uranus is Voyager 2, which flew past in January 1986. The spacecraft spent about 6 hours making its closest approach, during which it discovered 10 new moons, 2 new rings, and measured the planet's magnetic field, which turned out to be highly tilted and offset from the planet's center. Voyager 2's images of Uranus showed a featureless pale blue disk with little of the dynamic atmospheric banding visible on Jupiter and Saturn. The planet appeared almost eerily calm. We now know that Uranus has storms and atmospheric features, but they weren't obvious in the brief images captured during Voyager 2's rapid passage. Voyager 2 took 9 years to reach Uranus after its launch in 1977, arriving in January 1986. No mission has been back since. No mission to Uranus is currently approved, though there is strong scientific interest in a future Uranus orbiter that would study the planet in sustained detail. Neptune is the 8th and farthest planet from the Sun, orbiting at about 30 astronomutes, which works out to roughly 4.5 billion kilometers. Its closest approach to Earth is still about 4.3 billion kilometers. Neptune is also an ice giant, similar in composition and internal structure to Uranus, with a deep blue color that is even richer and deeper than Uranus's pale blue. The striking difference in color between the two ice giants, despite their similar compositions, is not fully understood. Neptune has the most dynamic atmosphere of any planet in the outer solar system. Its great dark spot, observed by Voyager 2 in 1989, was a storm system comparable in size to Earth. By the time the Hubble Space Telescope observed Neptune a few years later, the great dark spot had disappeared, replaced by new features. Neptune's atmosphere changes on surprisingly short timescales. Voyager 2 flew past Neptune in August 1989, completing the grand tour of all 4 gas giants that it had begun 12 years earlier when it launched in 1977. The journey from Earth to Neptune took 12 years of continuous flight, 12 years to cover 4.5 billion kilometers. Voyager 2 arrived at Neptune moving at about 20 kilometers per second relative to the Sun, flying past the planet and its moons in a brief window before continuing on its trajectory out of the solar system. It discovered 6 new moons, 2 new rings, and captured the first close-up images of Neptune and its largest moon, Triton. Triton is one of the most geologically active moons in the solar system, despite its extreme cold. Its surface temperature is about 38 Kelvin, minus 235 degrees Celsius, making it one of the coldest places we've visited. Yet Voyager 2 observed active geysers on Triton's surface, dark plumes of nitrogen gas erupting from beneath the surface and rising several kilometers into the thin atmosphere. The energy driving these geysers comes from sunlight absorbed by the dark material beneath the surface nitrogen ice, which warms slightly and vaporizes, building pressure until it erupts. Triton also orbits Neptune in the wrong direction, retrograde, opposite to Neptune's rotation and to the orbits of almost all other large moons in the solar system. This strongly suggests that Triton wasn't formed alongside Neptune, but was captured from elsewhere in the outer solar system, perhaps from the Kuiper belt. Being tidally decelerated by Neptune's gravity, Triton is slowly spiraling inward and in about 3.6 billion years it will come close enough to Neptune that tidal forces will tear it apart, forming a ring system that will be far more extensive than Saturn's. Neptune has not been visited since Voyager 2 in 1989. There is significant scientific interest in a future Neptune system mission, particularly one that would study Triton in detail. A Neptune orbiter with a Triton flyby, or even a Triton lander, would be extraordinarily scientifically valuable. But the journey time of roughly 12 years or more using currently available propulsion, combined with the cost and complexity of such a mission, has kept it in the proposal stage. A Neptune mission launched in the late 2030s or 2040s might arrive in the 2050s or beyond. Beyond Neptune lies the Kuiper Belt, a vast region of icy objects extending from about 30 to 50 astronomically from the Sun. The Kuiper Belt is named after Dutch-American astronomer Gerard Kuiper, who in 1951 predicted the existence of a population of primitive icy bodies beyond Neptune. The Kuiper Belt is similar in concept to the asteroid belt, but much larger and composed primarily of ice rather than rock and metal. It contains hundreds of thousands of objects larger than 100 kilometers across, and potentially billions of smaller ones. The largest known Kuiper Belt objects include Pluto, Eris, Makemake, and Haumea, all of which are large enough to be classified as dwarf planets. Pluto was discovered in 1930 by American astronomer Clyde Tombaugh and was classified as the 9th planet for 76 years until 2006, when the International Astronomical Union redefined the term planet in a way that excluded Pluto. The decision was controversial and remains so among some astronomers and much of the general public. But scientifically, the reclassification reflects a genuine insight. Pluto is not an anomalously small planet, but a large member of a class of objects, the Kuiper Belt objects, that number in the millions. Treating it as a full planet while ignoring the rest of the Kuiper Belt would be like calling Ceres a planet while ignoring all the other asteroids. Pluto orbits at an average distance of about 39 astronomities from the Sun, though its elliptical orbit takes it as close as 29 astronomities at perihelion and as far as 49 astronomities at aphelion. The New Horizons spacecraft, launched on January 19, 2006, took the most direct route ever flown to the outer solar system, using a gravity assist from Jupiter in February 2007 to boost its speed and reduce the total travel time. Even so, it took 9.5 years to reach Pluto, arriving on July 14, 2015. New Horizons flew past Pluto at about 50,000 kilometers per hour, too fast to enter orbit, capturing detailed images of the surface during the hours of closest approach. Those images were extraordinary. Before New Horizons, Pluto was just a blur in even the best telescopes, a faint point of light with some vague brightness variations across its face. After New Horizons, Pluto became a real world. It has mountains of water ice up to 3,500 meters high. It has a vast, nearly featureless plain of frozen nitrogen and carbon monoxide ice, informally named Tombaugh Regio, in honor of its discoverer, which is constantly being renewed and smoothed by convection in the nitrogen ice. It has a thin atmosphere of nitrogen that freezes and falls to the surface when Pluto moves far from the Sun and vaporizes when it comes closer. It has complex reddish-brown organic chemistry on its surface and in its atmosphere, and it has a large moon, Charon, that is so massive relative to Pluto that the two worlds orbit each other around a common center of mass that lies outside Pluto's surface, making them effectively a binary dwarf planet system. After completing the Pluto flyby, New Horizons continued deeper into the Kuiper Belt on a trajectory that carried it toward a second target, a small Kuiper Belt object called Arrokoth, which it flew past on January 1, 2019. Arrokoth, then nicknamed Ultima Thule, turned out to be a contact binary, two lobes that apparently formed separately and then gently came together at very low speeds. It looks like a snowman with two nearly spherical sections joined at a narrow neck. Arrokoth sits at about 44 astronomicals from the Sun, and New Horizons took 13 years to reach it from Earth. As of 2024, New Horizons is at about 57 astronomicals from the Sun and continuing outward, with its power supply gradually declining as the radioactive plutonium in its thermoelectric generators decays. At some point in the 2030s or 2040s, New Horizons will go silent, becoming another dark human artifact drifting through the outer solar system. Beyond the Kuiper Belt, beyond about 50 Ax-Daniel-Teuts, lies the scattered disk, a region of even more distant icy objects whose orbits have been perturbed by gravitational interactions with Neptune. Sedna, a remarkable dwarf planet discovered in 2003, has an orbit that takes it from about 76 astronomicals at its closest point to the Sun all the way out to about 937 astronomicals at its farthest, with an orbital period of roughly 11,400 years. No spacecraft has ever been anywhere near Sedna, and given its current distance of about 84 astronomicals and its trajectory, visiting it within our lifetimes would require either a very fast launch trajectory or waiting for it to come closer, which won't happen for many centuries. And beyond even the scattered disk, at distances of perhaps 2,000 to 100,000 astronomicals from the Sun, lies the Oort Cloud. The Oort Cloud has never been directly observed. Its existence is inferred from the long-period comets that occasionally fall into the inner solar system from nearly all directions. Long-period comets are thought to originate in the Oort Cloud, their orbits disturbed by gravitational nudges from passing stars or the galactic tide, sending them on plunging trajectories into the inner solar system, where they become visible as bright, tailed objects before swinging around the Sun and returning to the outer reaches. The Oort Cloud is believed to contain trillions of icy objects, the gravitationally loosely bound outer fringe of our solar system, extending nearly halfway to the nearest star. No spacecraft has ever reached the Oort Cloud, and none will within many human lifetimes. Voyager 1, the farthest human-made object, is currently at about 160 astronomicals from the Sun. It crossed the heliopause, the boundary between the Sun's influence and interstellar space, in 2012, making it the first human-made object to enter interstellar space. But at its current speed, it would take about 300 years to reach the inner boundary of the Oort Cloud and about 30,000 years to pass through its outer edge. And Voyager 1 is not headed toward any particular star. The nearest star it will come close to is Gliese 445, which it will pass within about 1.6 light-years in approximately 40,000 years. That's close by interstellar standards, but still an enormous distance. Gliese 445 won't capture Voyager 1. The spacecraft will simply drift past it and continue into the void, a silent artifact of a civilization that once existed around a small yellow star in an outer arm of the Milky Way. And this brings us finally to the stars. The distances involved in interstellar travel are of a completely different order from anything we've discussed so far. All the distances within our solar system, from the Moon to the Oort Cloud, are measured in hundreds or thousands of AU. The distance to the nearest star is measured in light-years, and 1 light-year is about 63,000 Ax-Daniel-Teuts. The jump from the solar system to the nearest star is a jump in scale of more than 2 orders of magnitude. It's not like going from one city to the next. It's like going from one city to the other side of the planet. The nearest star system to our Sun is Alpha Centauri, a triple star system that lies 4.37 light-years from Earth. Alpha Centauri A and B are two Sun-like stars that orbit each other with a period of about 80 years. Proxima Centauri is a small, dim red dwarf star that orbits the A-B pair at a much greater distance, roughly 15,000 astronucleads from them. Despite being gravitationally bound to the other two stars, Proxima Centauri is slightly closer to us than they are, at 4.24 light-years, making it the nearest individual star to the Sun. Proxima Centauri is known to have at least 3 planets. Proxima b was discovered in 2016 and orbits within Proxima Centauri's habitable zone, the range of distances where liquid water could potentially exist on a rocky surface. This was an exciting discovery that generated enormous public interest. Unfortunately, the excitement has been tempered by subsequent observations suggesting that Proxima b is subjected to intense ultraviolet and X-ray radiation from its parent star, which flares frequently. Whether Proxima b could have retained an atmosphere capable of supporting liquid water and life in the face of that radiation is deeply uncertain. But the mere fact that there's a potentially habitable zone planet at the nearest star is remarkable and gives us a target. So how long would it take to get to Proxima Centauri? At the speed of Voyager 1, about 17 kilometers per second relative to the Sun, the journey would take about 75,000 years. This is not a typo. 75,000 years. The entire history of anatomically modern humans spans only about 300,000 years. Neanderthals went extinct about 40,000 years ago. The oldest known cave paintings are about 45,000 years old. The last mammoths died on Wrangel Island in the Arctic about 4,000 years ago. Traveling at the speed of our fastest current spacecraft, you'd need a journey time equivalent to nearly the entire span of recorded human technology and more to reach the nearest star. If we could build a spacecraft capable of traveling at 1% of the speed of light, which is 3,000 kilometers per second or about 10.8 million kilometers per hour, the journey to Proxima Centauri would take about 424 years. That's still multiple human lifetimes. Nobody who launched on such a mission would live to see the destination. Even their grandchildren might not arrive. The crew that landed would be the descendants of the crew that departed, separated from the original explorers by many generations. If we could somehow reach 10% of the speed of light, the journey would take about 42 years, which is within a single human lifetime. A person who left Earth at age 30 might arrive at Proxima Centauri at age 72, old but alive. That would be the minimum threshold for what you might call a practical interstellar mission in human terms. A mission where the people who depart are the same people who arrive. But 10% of the speed of light is 30,000 kilometers per second, and no propulsion system we've built or seriously proposed could come close to achieving that speed for a crewed spacecraft of any useful size. At 20% of the speed of light, the journey would take about 21 years. At this point, an additional physical effect from Einstein's theory of special relativity starts to become noticeable. At velocities that are significant fractions of the speed of light, time actually passes more slowly for the traveler than for a stationary observer. This phenomenon is called time dilation. At 20% of the speed of light, the effect is small, about a 2% reduction in the rate at which time passes for the crew relative to Earth time. At 50% of the speed of light, the crew would age only 87% as fast as people on Earth. At 90% of the speed of light, the crew would age only 44% as fast. At 99% of the speed of light, the crew would age only 14% as fast. This means that if you could somehow travel at very high fractions of the speed of light, extremely long interstellar journeys could be accomplished within a single human lifetime for the crew, even though many decades or centuries would pass on Earth. A ship traveling at 99% of the speed of light could cross 100 light years in about 100 years of Earth time. But the crew would age only about 14 years during that journey. This relativistic time dilation is not a hypothetical effect. It's been confirmed experimentally many times in particle accelerators and with precise atomic clocks flown on aircraft. It's real physics. But it only becomes practically relevant at speeds that are far beyond anything we can achieve with current or near-future propulsion. The Breakthrough Starshot Initiative, announced in 2016 and funded by technology entrepreneur Yuri Milner with scientific leadership from Stephen Hawking before his death in 2018, proposes a possible path to interstellar probes within our century. The concept involves launching tiny spacecraft called light sails or starships, each weighing only a few grams. These miniaturized probes would be equipped with cameras, sensors, and communication systems packed into a chip the size of a postage stamp. They would be attached to a sail made of extremely thin, lightweight material. A ground-based array of powerful lasers would then focus their beams on the sail, accelerating the tiny probe to about 20% of the speed of light over the course of a few minutes. At 20% of the speed of light, such a probe could reach Proxima Centauri in about 20 years. After arriving in the system, it would spend only a few hours near the star and its planets before flying past at tremendous speed, unable to slow down. During those hours, it would take images and make measurements, then spend 4 years transmitting the data back to Earth at light speed. 40 years total from launch to data receipt to get our first close look at another star system. This is an audacious concept, and most of the technologies it requires don't yet exist in the required form. The laser array would need to generate about 100 gigawatts of power, comparable to many large power plants. The sail would need to reflect the laser light with extremely high efficiency, while withstanding enormous energy flux. The miniaturized spacecraft would need to survive the acceleration forces and then operate reliably after 20 years in interstellar space. None of these are insurmountable in principle, but none are easy, and the project is still in an early research phase. For human interstellar travel, the challenges are incomparably greater. A crewed ship would weigh millions of times more than a few grams. The same laser array that could push a gram-scale probe to 20% of light speed could push a crewed spacecraft to a tiny fraction of that speed. To accelerate a crewed spacecraft to even 1% of the speed of light would require an amount of energy comparable to humanity's entire current annual energy consumption. To decelerate it again at the destination would require the same amount, and then to accelerate it for the return journey and decelerate it again at Earth would require the same amount twice more. The total energy bill for a crewed round trip to the nearest star at 1% of the speed of light, using any propulsion system we currently understand, would be staggering beyond the capacity of any civilization we can realistically imagine building in the near future. Beyond propulsion, there's the challenge of sustaining human life for the entire journey. A ship traveling at 1% of light speed would take 424 years to reach Proxima Centauri. Even at 10% of light speed, the journey takes 42 years. In either case, you need not just a spacecraft but a closed ecological system capable of sustaining human life. Recycling all resources indefinitely, producing food, managing physical and mental health, and doing all of this in deep space, far from any help. The engineering challenges involved in a truly closed life support system are formidable. We have made progress with systems on the International Space Station, but the ISS is not fully closed. It receives regular resupply missions from Earth, and its crew cycles through every 6 months. A ship heading for another star gets no resupply missions. Every molecule of oxygen, every calorie of food, every liter of water has to be recycled or produced from the resources the ship carries. The psychological challenges of such a voyage are also profound. Imagine living your entire life inside a spaceship, knowing you will never see Earth with your own eyes, knowing your children and grandchildren will also live and die on the same ship, knowing the destination is something that exists only in data and photographs that were gathered decades before you were born. The social structures, the culture, the governance of such a vessel would have to be developed essentially from scratch, drawing on everything we know about isolated communities, but scaling up to a challenge that has no precedent in human history. There are concepts for addressing the timescale problem in different ways. One is the generation ship, which we've already mentioned, a vessel designed to carry multiple generations of humans who will live out their entire lives aboard the ship. The generation ship concept has been a staple of science fiction for nearly a century, explored in countless novels and stories. From a pure physics standpoint, there's nothing impossible about a generation ship. You could build a vessel large enough and well designed enough to sustain a viable human population for centuries. The challenges are engineering, social, and psychological rather than fundamental physics. But they're still enormous challenges, and no one has seriously proposed building a generation ship as a near-term project. Another concept is suspended animation or cryogenic hibernation, the idea of putting crew members into a state of dramatically reduced metabolism so they age very slowly during the voyage and can be revived upon arrival. Some animals, including certain bears, ground squirrels, and bats, can enter states of deep hibernation in which their metabolic rate drops to a tiny fraction of its normal level. Applying similar principles to humans would require understanding the biology of hibernation at a level we currently don't possess, and even then it's not clear that human metabolism could be safely reduced to the same degree as in natural hibernators. There's active research in therapeutic hypothermia, the deliberate cooling of patients to reduce metabolic rate during surgery or after cardiac arrest. But the durations involved are measured in hours, not decades. Taking a human being from normal body temperature and keeping them safely alive and unharmed for decades, then reviving them, is so far beyond current medical capabilities that it remains in the realm of speculation. A third concept is to send, not humans but their genetic material, frozen embryos or digitized genetic information, along with robotic systems capable of growing and raising children at the destination. This solves the problem of keeping adult humans alive for centuries, but raises profound ethical questions about creating children in an environment they had no choice about, raising them without parents in any conventional sense, and launching them into a life on a distant world they know nothing about. It's a concept that exists in science fiction, but would require deep ethical deliberation before any civilization seriously considered it. Beyond the nearest stars, the Milky Way galaxy is about 100,000 light-years across, containing somewhere between 100 and 400 billion stars. Most of those stars are between 2 and 10 light-years apart in our region of the galaxy, though the density varies enormously from the sparse outskirts to the crowded galactic center. Crossing the entire galaxy at the speed of current spacecraft would take hundreds of millions of years. Even at 10% of the speed of light, crossing the galaxy from one edge to the other would take 1 million years. The Andromeda Galaxy, the nearest large spiral galaxy to our own, and the most distant object visible to the naked eye from Earth, is about 2.5 million light-years away. At 10% of the speed of light, it would take 25 million years to reach it. At the speed of current spacecraft, more than 40 billion years, longer than the current age of the universe. These numbers make it clear that interstellar travel, at least at any scale beyond visiting the nearest few stars, is not just a technology problem that we'll solve eventually with enough time and effort. It may be a fundamental constraint imposed by the structure of the universe itself. The distances are simply so large and the energy requirements so enormous that it's genuinely unclear whether any civilization, no matter how advanced, could ever practically travel between galaxies or even between widely separated regions of the same galaxy. But that shouldn't dampen our spirits. Within our own solar system, we have extraordinary destinations waiting for us. 8 planets and their moons, dozens of dwarf planets, millions of asteroids, countless comets, and the vast outer reaches of the Kuiper Belt and Oort Cloud. Every one of these worlds is different from every other. Everyone has secrets to reveal about the formation and evolution of our solar system and about the conditions under which life can arise. The journey to Mars alone will be one of the greatest adventures in human history when it happens. The exploration of Europa's subsurface ocean could potentially reveal that life is not unique to Earth, which would be among the most important scientific discoveries ever made. The travel times are what they are. We cannot wish them away or engineer around the fundamental constraints of orbital mechanics and rocket propulsion. But within those constraints, we've already accomplished extraordinary things. We've put footprints on the moon, we've landed rovers on Mars, we've flown past every planet in the solar system. We've sent probes beyond the heliopause into true interstellar space. We've landed on asteroids and comets. We've returned samples from asteroids, from the moon, and from the solar wind itself. We've built a continuously inhabited outpost in Earth orbit that has been occupied without interruption since the year 2000. The next steps are clear, even if they're not easy. Return to the moon with humans and establish a permanent presence there. Send humans to Mars within the next generation. Develop robotic missions to study Europa, Titan, Enceladus, and the other worlds where conditions for life might exist. Build the telescopes and instruments needed to study the atmospheres of exoplanets in enough detail to search for biological signatures. And keep pushing the boundaries of propulsion technology, not because we expect to reach the stars next century, but because the long arc of technological progress bends in that direction, and the choices we make now will determine how far our descendants can ultimately go. The universe is vast. The distances are staggering. The travel times are measured in months, years, decades, and for the stars themselves, in centuries and millennia. But we are a species that has always moved toward the horizon, always pushed past what seemed like the limits of what was possible, always asked what's out there, and then built the machines to find out. The moon was once an impossible dream. Mars will be a destination within our lifetimes. The stars will be the challenge for generations yet unborn. The distances are vast. The travel times are long. The challenges are real and the obstacles are genuine, and sometimes they seem impossible. But the universe is patient, and so, in our own determined, stubborn, endlessly curious way, are we. Every spacecraft we launch carries with it not just instruments and science experiments, but the ancient human impulse to go somewhere new, to see something nobody has seen before, to push the edge of what's known just a little bit further into the dark. That impulse doesn't care how long the journey takes. It just keeps going 1 kilometer per second at a time, one mission at a time, one generation at a time, reaching for whatever comes next.